So we're looking at law of areas. So very first thing is, let's have a look at what it is and what it means. For that, we'll consider this as the sun. And I'll consider the planet is over here. After 20 days, it's over here. So this is 20-day journey. If I connect the planet to the sun, this is the area swept by this line, right? In this way. So this is the area swept by that line in 20 days. Now, if I take up another point, say this is day 0 and say this is day 20. This is 20 days. In this case, this is the area that is swept by this particular line. Now, if we compare this area, they will be equal. So if this is A1 and this is A2, A1 is equal to 8. This is the whole funda. That's your theorem basically. So as a consequence, we have the following thing. Let me show this. Okay, so this being the sun and that being the planet. See, please make your observation over here. It's not a very excellent animation or something, but it does the job. So point here that you had to observe was the planet when it's near to the sun, it's faster. As and when it goes away, it gets slower, and you can see that it's faster again. So I'm trying to move it. Can you see that? Can you see that? It's faster near and slows down. So that's the consequence of this theorem per se. That's what we are trying to prove. So how do we go on proving this? So let me give you guys a brief. See, very first thing is that we need to understand is sun and the planet being connected by, say, by a line. This is your radial component and that's your force, right? So the torque per se over here will be 0. The question is why? The torque will be 0. The torque on the planet will be 0. Why is the torque 0? Well, there is only one force that is acting on the planet. For example, in this case, in this system, there is only one force acting on the planet, that is the sun. So this source of the force is gravity. And gravity as a idea is a central force, center seeking force. So basically your R, as a consequence, R and F are collinear. They are collinear. How do I write collinear? Or 0 degree or 180 degree? Yeah, that's better. They're either 0 degree or 180 degree. In this case, it's 180 degree. But as a whole, what happens? The consequence is that your torque will be 0. Quite simple. Force, the only source of force on the planet is gravity because of the sun. And sun is always pointing towards its center. So torque will be 0, as simple as that. You guys agree? All I'm telling is torque on the planet is 0. Because torque is 0, what happens? As a consequence, your angular momentum what happens to angular momentum? Angular momentum will be constant. But why is that? This is because of fact that torque is given by rate of change of angular momentum. And since torque is 0, dl by dt will be 0. And if I integrate, I'll end up with this. On integrating, we'll end up with this relationship. So now, taking forward this fact, I can write one more relationship. What is that? Let's explore L. See, L is also given by R into P, or in vector form, it is R cross P. And momentum is given by mass into velocity. So if I rearrange, L by M is R times of V. But momentum is constant for this case, mass is also constant. So basically this is a constant. So R times of V. So from here, I need to somehow relate it to area. So from here, I need to jump to area. How will I do that? So end of it, just with the fact that torque is 0 on the planet, we ended up with this expression. Now we have to somehow relate this to area. How will I do that? See, if I take up a planet and after a very small duration, it has say moved set to this point. Okay, say the planet is moving in this way. So it has moved this way for a time interval of dt. So within dt, it has moved this much. So for a time interval, dt, we have this. Okay, so now the area over here is what? Area of this particular structure is half into base, into height. Do you guys agree? So what is the base? Base is this length covered. So length covered. Into height is, can I write height is almost the R? Height is R. For a very small time, whatever the structure is, it's almost this way. So this length and the neighboring length is almost same. Is it not? So if from trigonometry we can understand that they're almost same. So I'm writing this as R. How do you figure out the length covered? How do you figure out this length covered? I can make use of the velocity. So we know that length or distance is equal to velocity into time. Time is given dt times of r. So if I rearrange a bit, I'll get the following expression. And so on and so forth. I'm messing up the math over here as in representation and everything. But I'm just trying to show that on rearranging, we get an expression which looks similar to this. So if this entire expression is constant, so what can I tell? Half into a constant value and dt if I transpose dA by dt. So this entire thing is constant. It's a new constant, but still a constant. And dA by dt is a constant. That's it. Okay, so that's your basic idea. So you can take a minute, pause this. I'll show a bit more structured answer. For now, you guys can have a look, copy it. Okay, next. So what we have is a structured way to answer this. This is for your exam if you guys are interested. So we start off with the fact that we assume that planet moves under the gravitational force exerted by the sun. That's the only source of push or pull on the planet. So gravitational force is a central seeking force. As a consequence, the torque component is not present, only radial component is present in this setup. Right? So with this fact, our torque part will be 0 because R and F is 0. And with this, we can move on to relating angular momentum. And as a consequence, angular momentum is constant. And angular momentum is also given by that formula. And on rearranging, we get a constant. And we are taking this fact and substituting over here. Okay, so that's your distance part. What we saw, the distance that the arc region that the planet covers, that is that expression at the top. Okay, this expression basically. And moving on, we have using 2, we have this particular result. As a consequence, the rate of change of angle covered is constant, and we have Kepler's second law. So people who are interested can also have a look at this.